Good morning. Welcome to today's workshop. I'm Pen Fang. I'll be the chairman for this session. Our first speaker will be Harumiki Shimura. He will talk about multi-party quantum simultaneous message passing communication complexity. Okay, welcome.
Thank you for introduction. First, I thank the organizer to give me a chance to talk. This talk is based on the joint work with François Rugal in our university, or another Tel Aviv University, and Rotem Washington University. This topic is about communication complexity, which is a very well studied model in computational complexity. It's introduced by Yao, 1979. In this model, there are several parties. And in this figure, the party is 2. Alice and Bob. They have own input, and they can communicate each other. And finally, they want to output some functions value. Of course, possibly small amount of communication. This model has many applications to computational complexity lower bounds, such as VLSI, decision tree and data structure, Boolean circuit, etc., etc. These applications are written into a textbook of computational complexity, communication complexity, Kushilevich and Nissan, and Rao and Yadav. In the model of communication complexity, the most simplest model is simultaneous message passing model, so-called SMP model. This is the weakest model in communication complexity. The model is like this. And now we have K party plus level E. K party have each input XL, the party L, for example, n-bit string. And each party sends a message to referee. This is one way. And referee finally compute a function value. Referee does not have any information on the input of parties. Of course, the complexity, the cost is the total length of the message. This is a special kind of model in communication complexity, and it's studied in Yao 1979. The mode is various. The first studied deterministic classical mode. This must be output must be correct with exactly. Of course, in classical case, we can consider the randomized case. So that case, the referee can error with small probability. There are two kinds of randomized model. One is public coin. In this case, the parties have shared randomness. On the other hand, another model is private coin. In this case, these parties have no shared randomness. Both cases are well studied in communication complexity, but in distributed computing stuff, private coin is better because how public coins are shared to separate party. So possibly private coin is better to implement. Of course, the quantum SMP model and communication complexity was studied first also in Yao in 1993. Shared randomness and or entanglement model are allowed, but in this talk, we assume no shared randomness in quantum case. Now, I talk about the two-party SMP, the basic result. Of course, two-party case is very well studied in classical and quantum communication complexity. In particular, the famous and very well studied function is equality. This case, the party has input, for example, two-party case, Alice and Bob. These two inputs are same or not. This is the equality function. This function is very easy because in classical model and public coin model, then just constant number of bit is enough to communication. This is, you can use this kind of good code. This code is some original string to expand it to constant factor of length. So, and if the x and y is different, then the code value is very far from the perspective of having distance. Say the rate is at least 0.9. In that case, shared randomness is corresponding to the bit of this code string. And Alice send the JS bit of the code, also Bob JS bit of code to referee. And the referee check this equal or not. Of course, x equal y case, always referee output 1. On the other hand, if x not equal y, x is not equal y, the referee output 1 at the most 1/10 by the property of this. So the constant number of bit communication is enough. But the private coin case is much different. So now there is no shared randomness. This case, the omega root n is needed. It's shown by Newman and Segedi and Babai and Kine. Now I switch the quantum SMP. In quantum SMP has exponential advantage or equality if you consider the no shared resource. In quantum case, order log n qubit are enough, but in classical case, as I said, the omega root n is needed. This paper uses quantum fingerprint. This is roughly speaking very short, but available for checking whether x equal y. The technique is convert shared randomness protocol into the quantum fingerprinting. So this J and is superposed in the quantum state. After this result, more results are shown. For example, Yao show the Hamming distance problem. Also, quantum case is order log n, polynomial of order log n. But classical case is also, of course, more difficult than equality. So still lower bound is order root n. But in this case, the Hamming distance is at most d over not, where d is constant. It's important. And more two-party case is will be talked by Hasegawa-san tomorrow talk. Now I move to multi-party case. Of course, in classical case, multi-party SMP is studied a lot, but quantum case not well studied. Before our work, there is only one paper, Gavinsky one, in 2030. This result is negative. On the other hand, our result is positive. Now, I consider the question like this. Is quantum SMP efficient? Efficient means the logarithmic order of input length. When public coin SMP is efficient. For example, equality has efficient public coin SMP, order 1. So SMP also efficient, order log n by Barmaid. This question is yes in two-party case. Public coin SMP complexity is order 1, then quantum SMP with no shared resource is efficient, polynomial of log n. There are similar concepts to convert the public protocol to fingerprint protocol. So natural question is, this conversion hold for 3-party, 4-party? Unfortunately, no. So multi-party case, the Gavinsky et al. Show public coin SMP complexity is constant, but quantum SMP with no shared resource is not efficient. They consider this specific function called gap parity. This is the promised function if the string added by XOR of all parties n-bit string. Then Hamming weight is larger than 2/3 n times n, then 1. On the other hand, if it is smaller than at most n over 3, then the function value is there. This problem is clearly have constant communication complexity in public coin because just share the JS bit and send each party JS bit of input and check the referees take the XOR. On the other hand, Gavinsky et al. Show the quantum lower bound k times n to 1 minus 2 over k. So K is 3 case. This is the order n to omega 1. So not the polynomial of log n, not efficient. So the next question is, for which problems efficient multi-party QS quantum SMP can be constructed from public coin SMP? So our result is not general, but we show the efficient multi-party SMP protocol for many function or problem. Equality function, frequency moment based on equality, neighborhood diversity, et al. In fact, our result is like this. So the main complexity is total complexity, but the local complexity is divided by k. So this quantity is order log for each party. Of course, classical case is k times root n. So the local complexity is root n. So exponentially better in n. To obtain our result, we used only one quantum technique, conversion from efficient decision tree based on modified equality query to efficient multi-party SMP. I explained this. This query is called MEQ. This considered by referees. Referee want to calculate given index ij, it's in the k parties index, and also n-bit string, 2 n-bit string y and z. Now, referee want to compute the string of ith party XORed y equal jth party's input XORed z. This is a modified equality. The point is each player must send state without knowing query by referee. This is the point. We can show this lemma. There are fingerprint of order log n qubit, such that else player send a state, this type of fingerprint to referee who can compute modified equality query function successfully. This proof is a kind of the modification of Berman et al. Fingerprinting technique. But our case, we use constant rate good and linear error correcting code because we need to modify from the fingerprint of XL to fingerprint of XL XORed Y by referee. So we need this kind of error correcting. Now we consider more difficult task by referee. It's a modified equality decision tree. So this case, referee want to compute like this. First, check the x1 equal x2. This case, this first index is 1 and second index is 2. This part is 0, 0. And if yes, then yes is maybe right child here. And or otherwise left child. If this child come, then next MEQ is 1, 3, 0n, 0 to n, and 0 to n. And here, if the algorithm come to here, then 1, 4, so first party and fourth party, but the second, fourth index is all 1, so x4, XOR all 1 string. This is equal 1. Finally, we get the value by distance. Now, our theorem, which is useful for our later application, any MEQ decision tree of depth D by the referee can be implemented by a party QMSNP with error probability delta that use order k times log D plus log 1 over delta times log n. So each party send this amount of qubit. So depth is small, then this factor is log. So essentially, logarithmic in input length. It's efficient. This proof is based on the lemma I mentioned, fingerprint. And this fingerprint is reused many times. And we use some kind of gentle measurement type lemma. In fact, we use the Gauss quantum union bound. So fingerprint test by swap test with very, very high probability by reverse the such a unitary operation. This kind of the some kind of projection. So and the result measurement state does not change much. And repeated, we can use such a quantum fingerprint. This is a proof idea. Now I show the application. First application is the grouping by equality. This is the K party, and the K party have each n bit string and partition of input by equality. For example, K equals 3 case, x1 is 0, 0, 0, 0, x2 is 1, 0, 0, 1, x3 is 1, 0, 0, 1. In that case, the grouping is 1 and 2, 3. So output is this. Now this is clearly solved by equality-based decision tree of depth k choose 2. So k party here and take 2, the pattern is k choose 2. So for example, k equals 3 case like this. First, x1 equal x2. Second, if 0, x1 equal x3. and like that. So depth is this. Now we can use this conversion lemma, conversion theorem. Now large D is K to 2. So cost is K times log K. Of course, delta is some very small constant. This is the cost of this problem. It's efficient in N. And corollary, as a corollary, we have quantum SMP protocol of cost K times log K times log N, or whether all input are equal, or there is whether there is a pair ij such that ith party input equal jth party. As another corollary, we can consider the P3-induced subgraph freeness graph. Now, I introduce some special case of multi-party SMP in graph. It's called NIH number in hand network. In this case, input length N is equal to the number of party K. Here, each party is a node of K-node graph G and has neighborhood vector of G as input. For example, this case is K is 5. 1 is neighborhood 2 or 2 and 4. So the neighborhood vector is like this. 2 and 4 is 1. 2 case 1 and 4 is neighborhood, so 1 and 4 is 1, like that. This is NIH network. The goal is really solve some problem on G. Now we consider the problem P3 induced subgraph, the graph. Now graph has the P3 induced subgraph free or not P3 subgraph induced subgraph free. In this graph is not P3 induced subgraph free because this induced graph is P3, so not free. On the other hand, this graph is P3 induced subgraph free. For example, we can take these 3, but this part is the C3, not P3. This problem can be reduced to group by equality because this simple observation exists. P3 induced free, a graph is P3 induced free if and only if it is a collection of node disjoint clique, or like this. So this case is 3 clique and 2 clique. In this case, the neighborhood vector can change to like flip the own input. For example, 1 is flip the own input part. 2 is also second part, like this. Then 1 to 4 are the same string. And 3 and 5, same string. So we can reduce to grouping by equality. So the exchange protocol exists. Now, second application is neighborhood diversity. In this case, we consider the twin concept of twin. Two nodes UV are called twin if the neighborhood vector is equal, or neighborhood vector minus v or u. So false twin or true twin. In that case, the two nodes are false twin. A graph has neighborhood diversity D if its node can be partitioned into D set, but no fewer such that all nodes in each set are twins of one another. For example, this graph has neighborhood diversity 5 because 1 and 2, 3. This 2, 3 has a true twin. And 4, 5. This neighborhood is 1 and 6, and each other disjoint. So does not connect. So this is false twin. And 6, and other 7, 8, 9. So the neighborhood diversity is 5. To check the neighborhood diversity, we can use this kind of modified equality way. So exactly neighborhood vector is equal or flip on bit, which check the true twin. This part is false twin. To check the all K-choose 2 pattern. So this again efficient protocol for this. Third application is the P4 induced subgraph freeness. This case also we have the efficient protocol, same quantity. But this a bit difficult rather than P3 induced graph. The key point is the characterization of P4 induced subgraph free graph exists. This characterization is the existence of decomposition, a sequence of nodes V1, V2, blah, blah, Vk, such that for each J, one of the following is the following fold. Vj has true twin in the graph G induced the subset Vk to Vj to Vk, or Vj has false twin in the same graph. So this kind of characterization is considered as a local change of graph by removing one a node one by one. And once we have this characterization, this essentially we can check the equality, modified equality. So this decomposition can be described two family of binary vector AV and EV updated sequentially and checking the following type of way. So we obtain the same quantity by this. The final application is the enumeration of isolated clique. The clique enumeration is very important and is well studied complex networks analysis. So some researcher considered the approximate version of this so-called isolated pseudo-clique enumeration. It's like this. So it's not complete clique. So this node connected to this node connected to this, but it's very close to the isolated clique. So this KHMM 09 paper considered max isolated creep as a many kind one pattern of such a approximation. A subgraph S of G is called max D isolated creep if the subgraph induced by S subgraph S is creep. And each node in S has at most D edge to outside. For example, this graph, this is the induced subgraph by S is clique and outside is 1. So this case max 1 isolated key. We show there is also QSMP protocol of cost k times d times log k squared for enumerating all the max d isolated key. So if d is constant, then the this quantity is efficient. The proof key point is we use the query on Hamming distance instead of equality. But in fact, this Hamming distance also can be computed by modified equality decision tree of depth order N2D. So if D is constant, then okay, by conversion by theorem, our theorem. Essentially, this check the like this. So this is really click, and for example, D equal 1 case, just one outside edge. So all the neighborhood vector is very close from the viewpoint of Hamming distance. So locally flip, for example, +2 like that, and check the equality. This is enough to check the this max isolated clique. Now I summarize my talk. This is the result for our summarize our result. We show several problems, quantum efficient protocol compared to classical case. The key point is the conversion from efficient decision tree based on modified EQ query to efficient multi-party QSMP protocol. Rough message is if your problem reduced to modified EQ query, you can find an efficient QSMP protocol. Thank you.
Okay, thanks for the great talk. So, okay, Masahito has a question here.
I could not understand the essence of this talk. So, simultaneously message transmission you are considering. So, initially you mentioned that there is some quantum exponential improvement, but I could not understand why classical case has so much cost. So, I could not understand the task. So, why classical case requires so much task communication?
So maybe it's part I skipped. The fundamental result is this, I think. So classical case, if no shared randomness is no shared randomness case, and the protocol the each party must send the many bit to for compute equality function. because not because this in this case we can use a shared randomness J, and using the J, the bit code the each bit is equal or not. But if this shared randomness does not exist, it's not easy to check the each party's input are equal or not.
So I cannot, still I cannot understand. So now you are considering the equality mx and my, they are equal or not.
Yeah.
So of course, if we have no shared randomness, we have to send all bit information. So Alice and Bob need to send all bit information for that message. But if they share shared randomness, I could not understand what they can do. Could you explain again if they have some shared randomness?
Shared randomness exists, then the Alice and Bob share some random bit, random index from 1 to ck. This ck, cn is the length of the good code, error correcting code. And this code has this property. So if the input x and y are different, the Hamming distance is very large. So constant rate. So if randomly choose j, then j's bit of ex and ey must be different with high probability. You understand?
I cannot understand. So J describes some index and randomly they choose the index.
Yes.
So, but this is a pretty shared randomness.
Yes, pre-shared randomness. Pre-shared randomness, J is there in the before in the protocol, and using this J, I send J's bit of EX, Bob send E bit of EY. Then they can check they are equal or not. If equal is referee output 1, otherwise output 0. Of course, x equal y case, referee always output 1. On the other hand, if x is not equal y, then the rate is 0.9. So randomly choose with 9, at least 9/10. The jth bit of ex must be different from jth bit of ey. So when x is not equal y, the referee output 0 with probability at least 9/10. So
So if they do not have shared randomness, Alice and Bob send the, for example, first bit and second bit and third bit. That protocol does not work.
If the shared randomness does not exist, this protocol cannot be used. So you need different idea.
But for example, Alice and Bob send the first bit and second round, they send the second bit. Why this method does not work?
So you mean that all the bit to send, then
No. One by one. So Alice send the first bit, and then they couldn't.
No. This is one way and only one round.
Only one round. So in that case, Alice and Bob send only first bit. Why this method doesn't work?
So if only first bit, then second bit is different, and first bit is equal. This case completely failed.
But if that's kind of random choice, why this works so well? I'm very confused.
So you don't have shared randomness. So random choice is not easy. So A and B does not, it's not easy to choose the same index.
But in that case, first bit and second bit, or maybe first and second.
First bit and second bit is okay. But in that case, if X and Y is different at third bit, it's completely failed.
But in the case of random choice, sometimes they fail to the different path.
So,
Why random choice works well? I'm very confused because random choice is J1 first one and second is J2, but sometimes the different bit is different place. Why this method works?
why this method? What do you mean?
This method is this random choice. Why random choice works well? So how you obtain that 9/10? So how did you get?
Public coin case. Public
Yes,
coin is clearly, so random choice is taken by shared randomness.
Of course.
So the Alice and Bob can choose the same index, jth bit of EX and jth bit of EY. This is the point.
But sometimes different bit is exist in the different point, not J. So for example, J prime, only J prime is different. There is that situation.
So in fact, this case is the we consider worst input. So we must output the correct answer with high probability for every choice of input. So if you choose each random bit for A and B without shared randomness, it's not so easy to get the same point if you send many bits, as long as you send many bits.
I cannot understand, and also I cannot find why you have a 9/10.
I think this is not so difficult. So maybe you must understand this. Because just A and B shared J, and send the jth bit of X and Y, and this property. So if X is not Y, then jth bit of X is not equal jth bit of Y with high probability.
Now you are considering you randomly choose.
So this random choose is prepared in advance.
So in that case, firstly you pick the different random key, right? Then later you randomly choose J. So in that case, maybe you have that. But if clearly decide that the choice of the check place, so then later, if we consider the worst case of the choice of X and Y, so then this
I cannot hear, so maybe internet connection is not good.
Of course, this is a kind of some topic because so firstly fix the choice of J, then later you consider the worst case of the X and Y. So in that case, your protocol doesn't work.
I don't understand. What?
Okay, so maybe we can put this question for later discussion. So ready time for second talk.
Tomorrow, Hasegawa-san talk about two-party SMP, so you can ask again to Hasegawa-san same question.
Okay, so maybe let's thank the speaker Haramuchi again. So
Thank you.
okay, thank you. So guess it's time for the second talk. So is the speaker here? Takeshi, are you here? Takeshi?
これって、あ、そうか。これ。Yeah, he's at Nagoya. Please wait.
Okay, so okay, can you maybe share your screen? So Takeshi, can you maybe share your screen? Can you hear me?
Yes, please wait a moment.
Okay, sure. Okay, good. So we can see your screen now. So our next speaker is Takeshi Kimura from Nagoya side, and he will talk about EM algorithm for quantum quantum machine. Okay, let's welcome.
Hello everyone. My name is Takeshi Kimura, a PhD student from Nagoya University. Today I will present our work on an EM algorithm for quantum Boltzmann machines in collaboration with Kotaro Kato and Masahito Hayashi. So let's start with some background in quantum machine learning. The main goal in this field is to leverage quantum resource to gain advantage over classical machine learning. There are several approaches to this. For example, a variational quantum eigensolver or VQE use variational circuits for optimization tasks. Another prominent model is the quantum Boltzmann machine or QBM, which is a quantum extension of the classical Boltzmann machine. Our work fits within a hybrid quantum classical approach. We use a quantum system to represent a model. Then we use a classical computer to optimize the model's parameters. This allows us to combine the exponential power of quantum model with the efficiency of classical optimization. This diagram illustrates our hybrid workflow. First, we use a set of classical parameters, which we call theta, to prepare a quantum state in the quantum system. We then perform measurements on this state. The measurement results are fed into the classical system. Here we calculate a cost function, like the scale divergence, to see how well our model is performing. Based on this cost, we update the parameters theta to minimize the cost function. These new parameters are then fed back into the quantum system to start the next iteration. This loop continues until the model is sufficiently trained. The conventional method for training models is the gradient descent or GD method. The objective is to minimize the Kerr divergence between true data distribution, PV, and our model's distribution, PV theta. The algorithm works by updating the parameters in the opposite direction of the gradient of the K divergence. It's scaled by a learning rate eta. However, GD method has several well-known issues. For non-convex functions, convergence to the global optima isn't guaranteed. Most critically, it is susceptible to a problem known as vanishing gradients. The vanishing gradient problem is particularly severe in quantum machine learning, where it's often called the barren plateau problem. As shown in the graph on the right, in a barren plateau, the landscape of the cost function becomes extremely flat. This means the gradient becomes exponentially small, causing the training to stagnate completely. This issue is known to be caused by several factors, including deep quantum circuits, the use of many qubits, high level of entanglement, and global cost functions. Since gradient-based methods rely on the gradient to learn, they are heavily impacted by this problem. So given the challenge of gradient descent, we propose a different approach. Instead of GD, we use the EM algorithm, which is an information geometric generalization of famous Pareto EM algorithm. The EM algorithm works by iteratively performed two steps, an E step and an M step. The crucial advantage is that the gradient method is only used for the M step, which is a convex optimization problem. By working with a convex substep, we have the potential to avoid the barren plateau. To understand one method, let's quickly review the model we are using. We start with the classical Boltzmann machine, which is an energy-based gradient generating model. It consists of two layers of units, a visible layer that corresponds to the data we can see, and a hidden layer that helps capture complex correlations. In this talk, we focus on a specific type called the restricted Boltzmann machine, or RBM, where there are no connections within a layer. In an RBM, the energy function of configuration of visible and hidden units is defined by this function, which depends on the bias and the coupling strengths between the layers. The probability of any given configuration is then exponentially related to its energy. By summing over all possible hidden unit configurations, we get the probability distribution of the visible data. Now let's move to the quantum case. The restricted quantum Boltzmann machine, or RQAPM, is a quantum extension of the RBM. Instead of an energy function, we have a Hamiltonian operator. This Hamiltonian includes the classical interaction terms, but now also contains transverse field terms, the sigma x terms, which introduce quantum effect. The probability distribution is obtained by taking stress of the system's density matrix with a projector for a given state lambda v. Let's formalize the problem setting in our work. We are working within the framework of unsupervised learning for Boltzmann machines. The primary objective is to fit a model distribution denoted as PV theta to a given data distribution PV. The model distribution is described by Boltzmann machine. The training process involves updating the model's parameter theta to make these two distributions as close as possible. To quantify this closeness, we use the clear divergence. The goal of the learning process is to minimize the value of this scale divergence as defined by the equation on the slide. An alternative to gradient descent is the expectation maximization algorithm. CEM algorithm directly works with the structure of the observed given variables to optimize the model. It alternates between two steps. On step, try to infer the hidden variables. And on M step, try to maximize the expected log likelihood. A key benefit is that the M step is a complex optimization problem. However, as noted on the slide, applying the standard EM algorithm directly to quantum Boltzmann machine is not straightforward. So let's introduce our proposed solution, GEM algorithm. This is an information geometric reformulation of the well-known upper beta EM algorithm, uppercase EM algorithm. To understand this framework, we need to talk about two families or sets of probability distributions. First is the exponential family. This is a set of probability distribution that can be written in a specific exponential form. You can think of this as the space where our model, the Boltzmann machine, lives. Second is the mixture family. This is a set of distribution formed by mixing or taking a weighted average of several component distributions. This family can represent the data distribution we are trying to run. The goal is to find the points on these two manifolds that are closest to each other, as measured by the KL divergence. The algorithm achieves this through alternating projections. Starting with an initial model Qt in the exponential family, step projects it onto the mixture family to find the closest point Pt. This projection minimizes the KL divergence from P to Qt. Then GM step projects this new point Pt back onto the exponential family to find Qt plus 1. This projection minimizes KL divergence from Pt to Q. This process is guaranteed to monotonically decrease the KL divergence at each step, ensuring stable convergence. And importantly, GM step is a convex optimization problem. Now we extend EM algorithm. This brings us to the quantum EM algorithm. The core idea is exactly the same, but we are working with quantum states which are described by density matrix. We again define two families. The exponential family is a set of quantum states defined by an exponential form involving a Hamiltonian. The mixture family is defined as a set of all quantum states that matches the measurement results we have from our data. Essentially, we are translating each classical concept into its quantum analog to build the quantum version of the algorithm. Our objective is to minimize the KL divergence between a state rho from the mixture family and a state sigma from exponential family. The algorithm works by alternating projections between these two families of quantum states. The step projects our current model state, sigma t, onto the mixture family to find the closest state, rho t. GM step then projects that state, rho t, back onto the exponential family to find our updated model, sigma t plus 1. The convergence is still monotonic, and the M step remains a convex optimization problem. Now, we apply this quantum EM algorithm to a specific model, the same quantum RBM, YSK RBM. And this is a special type of QBM where the visible units are classical, described only by Paris-Z operator, while the hidden units are fully quantum, described by both Paris-Z and Paris operators. This hybrid structure is key. This semi-quantum structure provides several key advantages. First, it has an analytical tractability, allowing for closed-form expressions for output probabilities and their gradients. Second, it has practical benefits. Because there is no entanglement between the classical visual and quantum hidden layers, it helps mitigate the prime plateau problem. This model has already shown strong performance on various datasets. Here is how we formally define the EM algorithm for the SQRBM. The exponential family script E is simply the set of all possible quantum states or SQRBM model can produce. The mixture family script M is constructed based on our target data distribution PV. It consists of states where the probability of measuring a visible state V matches the data probability DVV. The objective is to minimize the Kerr divergence between these two families, which can be decomposed into two terms as shown at the bottom. This leads to our final algorithm. For each iteration, we perform two steps. Each step is simple. The optimal choice for the hidden state is simply the hidden state of our current model. The M step then becomes a convex optimization problem to find the next set of parameters theta. We can solve this step using a standard method like gradient descent. But remember, this GDD is now being applied to a convex problem, so we don't have to worry about local minima or the barren plateau issue within this step. So to summarize how our approach mitigates the barren plateau problem, it's a two-part solution. First, from the model aspect, we use the SQRBM. Its hybrid structure prevents entanglement between the layers, which structurally avoids the key cause of vanishing gradients. Second, from the learning model aspect, we use the EM algorithm. Its M step is convex optimization problem, which provides a well-defined path towards the minima and ensures stable learning, helping to escape the flat landscape. So we tested our method against the standard standard gradient descent approach on several datasets. In these plots, YM algorithm is shown in blue, and the standard GD method is in red. The y-axis is the Kerr divergence, so lower is better. On the Bernoulli dataset, you can see the blue lines consistently achieve a lower final KLD than the red lines for different number of hidden units. On the parity dataset, the result is same. On the culinary dataset, the standard GD method performs slightly better, which is something we are investing further. And finally, on the ON2 dataset, OIM algorithm again shows the superior performance. In conclusion, we have proposed a novel training method for quantum Boltzmann machine using the GEM algorithm. We applied this to the SQLVM, which allowed for analytical update rules and demonstrated stable and effective learning. Our combined approach has the potential to avoid the parent plateau problem. Our method outperforms standard GED in 3 out of the 4 test cases in experiments. One current limitation is the convergence speed. For future work, we plan to explore methods to accelerate the complex M step, and we also aim to extend this framework to fully quantum RPMs. This concludes my presentation. Thank you for your attention.
Okay, thanks for the great talk. Is there any questions? Okay, so maybe I can ask the one big question. So, is this algorithm to run on quantum computers or on classical computers? So, can you hear me?
Sorry, could you please repeat? To run
So, is the algorithm run on quantum computers or on classical computers? I'm a bit confused.
a quantum
Yes.
computer?
So the input state rho and sigma on quantum state, not density matrix. Can you hear me?
So you asked about you are asking about the measure of quantum state.
So you call this algorithm quantum EM algorithm. I'm wondering, is this a algorithm for quantum computers or for classical computers? So the input state is quantum signals or density matrices.
In this work, we did it in classical computer, classical simulation, but in future work,
Okay, it's okay. So maybe we can discuss later. So yes. Okay. Okay. Thanks. This is clear. Is there any other questions? Oh, okay. So there's another question here.
What kind of task this model can do? Like what kind of data?
The first task, the task is we need to simulate a classical system by using quantum computer. Quantum computer means that some hidden quantum system. By using a hidden quantum system, we want to simulate classical behavior.
Like some classical physical system.
Classical physical system, yes, classical. So then we can use this one for the conventional task. So,
Thank you.
Good. So if there's no further questions, so let's thank the speaker again. Okay. Okay, so I guess it's time now. So our next speaker is Sanjay Ghosh from Shenzhen side, and he will talk about quantum reservoir processing for quantum neural network perspectives. Let's welcome.
Thank you very much. And I would like to thank Professor Hayase for inviting me. It is nice. So let me talk about one of the topic that we are working on, which is processing. And so this is the outline of the talk. So first I will show some of the tasks that processor can do, including copy, state preparation, also so, in general, neural network, when we are talking about neural network, the most famous one is neural network, where we would see that there are neural nodes which are nonlinear depth, and they have a function which is nonlinear. Then they have connections between the neural nodes, and these connections are in this case feed forward, meaning that the information can go. Let's just here to the next layer. And this is the feed forward time network, and these are in this case the connections are unidirectional. As I said, the information can go forward. So this is a good for static data processing. For training, we often use technique like back propagation. And there is another type of neural network which is more similar to how our brain functions. So in our brain, it is certain that these neural networks are not like this one. Like doesn't only go in the forward direction, but in fact the information can go back and forth there. Be loop in the same neural node. And so these kind of neural network are the connections are bidirectional, meaning that information can flow in both directions. And this is because of this bidirectional nature, and it can have a sense of dynamics inside the network. And this is why it is good for dynamical data processing. However, the problem with such a neural network is that the training can become very difficult because this is a nonlinear system and also dynamical system now. And therefore, the dynamics inside this neural network can be quite chaotic because it's a nonlinear system, and also can have properties like bifurcation and so on. So it can be then the solution for this problem came in the form of what now people call reservoir computing. So the idea came from this observation that if you have a large neural network and which has this recurrent nature, then they observe that you do not even need to train all the connections. You can keep the most of the connections random, and then only train a single layer at the output level. So this is the structure of this neural network, and this is the input layer, and then it goes to a big, large recurrent layer where the information has dynamical nature, and then the readout is taken from this. This readout is then connected to the last layer, the output layer, and only this connection between these two layers is trained. So in this case, the advantage is that it keeps the dynamics, that is the recurrent nature, whereas in the problem of the training is now solved because only the output layer needs to be trained, and this is a single layer, and these connections are taken as feed forward. So this layer is very simple and has no need for back propagation. There is no barren plateau at all. There is a single layer training, and it's also hardware friendly because whole this part is it doesn't need to train. This system can be any system, and people have implemented the optical system, electronic system, and now we will discuss that this part of the network. So why this? How this reservoir computer works? So suppose that I have this. I can be anything. It can be it's classical anything. That X goes into this reservoir. That is a big large. Then this thing, what it does is that it takes this smaller dimensional input and expand it into a large dimensional. Then then we read the what is the information and read out from this large. This is the xi, capital Xi. And then the final output will be given by this yi, that is equal to matrix, this matrix times the xi, that is the beta. So, and this, as we can see, we have to learn what is this W. And this learning W is basically a linear reciprocal. So, meaning that I will have a lot of X, a lot of Y, and they will have some points. And imagine that it's a multidimensional space. I'm representing it in a two-dimension, but actually this is a multidimensional. X is a multidimensional. And so these points, and then we treat all these points with this formula. And this formula, and the W is basically the slope of this line. And so mathematically, this regression is done by this formula that we have this y and x. In this case, y is known because we are training at the moment, and then x is the readout. And then by this formula, which is called the regression, then we will get the W and the matrix, training matrix. So obviously, this is a very easy, computationally relatively easy task that you have multiplication and inversion. Beta is a small regularization parameter. Usually, it's taken very small number. Because our data set is often overcomplete, so the W, if we do not so then why a quantum computer, a quantum system? Because quantum system has high dimensionality. So as we discussed previously, the reservoir need to be a higher dimensional system, and the interconnection can be established through entanglement or superposition. And finally, nonlinearity can emerge from discrete quantum levels like however, the quantum system often has the problem of loss, etc., and also difficult to find useful quantum algorithm that suppose I have a task to do. What is the best quantum algorithm that gives? So in this case, if we take this route of reservoir computing, because it's a neural network, so it is training-based network, training-based paradigm. So therefore, it can tolerate disorder, noise, and incoherence, etc. And it's also versatile platform because it learned from the example. So therefore, you do not need to have an algorithm like. So let me show some of the examples that people have done. So first types are quantum reservoir for classical data processing. So this was one of the first examples came from actually Japan, Tokyo University. So what they showed that if we take instead of a classical neural network, if we take a quantum chain, a quantum spin chain recommended by this Hamiltonian, that is this a bunch of spin other, and then they can inject classical data through this So they can inject by modulating the classical field, inject the information into the system, and then the system will evolve, time evolve, and then it is a dynamical system, and then after that they will measure the spin projection, which is equivalent to sigma z measurement. So that is their readout, and then what they show is that what they can achieve with 5 to 7 qubits. They need a classical neural network of 100 to 500 nodes to match the same accuracy. So they typically perform tasks like data time series prediction. So what they identified is that this advantage, what they got this advantage is because of the large user space of the system, put for him, and so they can map their data into a much higher dimensional system. So, and we performed similar study, and this is the number of qubit we need, and this is the number of classical nodes we need to achieve the same level of accuracy for image recognition. So we take this MNIST data recognition problem, and so we compare the number of quantum node we need and number of classical node we need. For the classical, the quantum node is of the order of 1 to 3, whereas the classical nodes we require for the same level of accuracy is 100. We find that the classical node required is actually exponentially large. Then we actually move to the quantum situation. So we then thought that can it process quantum information instead of classical information. Here we introduce that this similar Hamiltonian, that there are a bunch of quantum nodes, and these quantum nodes are two-level system like qubit, and then the input is a physical quantum state. For example, it can be photons encoding in quantum information, and that goes into this qubit system or two-level quantum systems, and then these connections in between the two-level quantum systems are completely random, and so that absorbs this quantum state, and then it will evolve according to the Schrodinger equation. And then at the end of some evolution, we will measure the sigma z measurement. That is the number of excitation in each quantum. And that is our the readout, and then we will multiply with this matrix, and we will get the final output. And if we include the loss and some quantum error, etc., it can be represented by this quantum master equation. That is what we do. And then this is the a task that we tried. That suppose I say a unsorted quantum states, half of them are entangled, and half 50% chance that they are separable. And then the task of this network is to sort out which state is entangled and which one is separable. So we assign that the final output is will be 1, 0 for entangled states and 0, 1 for separable states. And this color code is actually the prediction by the network, and this axis, actually radial axis, is the symplectic eigenvalue of this bipartite Gaussian states. And so we see that there is this is the theoretical boundary, this circle, and this is the color code is predicted by the network. So the so the network is correctly identified that which states are entangled. And we tried with different types of Gaussian states, for example, thermal state, photon added state, photon subtracted state, or simply like states or bound entangled state, and we tested with this all this kind of state to see the high level of accuracy of prediction. then we tried another, the quantitative estimation. So the previous example was classification of quantum states. So here we wanted to know whether the network can do some quantum estimation. And this is there where we train the network to estimate, for example, negativity for by states and or entropy or nonlinear properties of the density of states, something like trace of root to the power n, and n can be something like the purity and then higher order nonlinear. So we see that this is the prediction. So this is the true value of this quantity, each of this quantity, and this is the prediction. And if they are equal, the true value is equal to the prediction, then they will follow this black line. And these points are the prediction by the network. And you can see there are two. We tried with network nodes, 2 qubit and 4 qubit, and we see that the accuracy is very good for different quantities. And then we tested what is the role of the decoherence, and we see that we introduce the decoherence term in the master equation and tried what will happen if we increase the decoherence rate successively. We see that when the decoherence rate is small, and then the network is working and it can distinguish separable and entangled states. And as we increase the decoherence rate, the prediction ability becomes weaker and weaker, and at the end there is no prediction. That's random, completely random prediction. And then the last year we did a work and we compare it with the shadow estimation, because we did some quantum estimation. And the shadow estimation is one of the famous quantum estimation method. So what we wanted to know is that what is the efficiency, like which one works better and need less resource. And so we estimated this variance upper bound for the two methods, and we see that this is the reservoir. The blue this green is the reservoir computing, this reservoir processing, and shadow estimation. So if so the variance upper bound for the reservoir processing is slightly higher than the shadow norm, and so therefore we need more resource for this reservoir. But if we see the comparison, if we take the ratio, they are very close to 1. So the resource needed is almost same, a little bit higher. But if we compare the number of settings for the shadow estimation, if we have larger qubit states, then the number of settings we need is actually increasing. Whereas for our case, actually we need only a single setting, because as we explained, that there is no need to change the setting at any point for this network. So I would like to, because we were very successful in quantum estimation, so we wanted to know whether we can do the full quantum state tomography. So as we know, the quantum state tomography is a systematic method to know the density matrix of a quantum state. And it is this tomography is actually is similar to what we do in medical imaging. That if we have a higher dimensional system, and if we have a camera which can take only 2-dimensional picture, then to get the full view of the higher dimensional picture, we take a lot of measurement, a lot of picture from. And so similarly for quantum states, because we have a lot of elements in the density of matrix, and they are independent, and so we have to measure various all the diagonal and diagonal elements of the row, and to do that we need to have different settings. So this and the number of setup we require for a n qubit is actually exponentially large, like 2 to the power n. So the many qubit tomography is quite difficult, and experimentally many qubit tomography is quite limited. So here we wanted to use a quantum reservoir because here we need only one setup. And the reason is that we keep the same as before. We send the input, and that goes to the reservoir, and then we take the measurement in each nodes, and then we assign that the output need to be the density matrix. This is our hope that we can do. And we can apply it for continuous variable system or discrete tomography, and the same system should work if we can. So here we tested and actually it can do this tomography. However, a key question is that how many quantum nodes we need. And it turns out that we need actually exponentially large number of quantum nodes. Because we need, if we have a like n qubit in the input state, then we need for n number of measurement outcomes to estimate the density matrix. However, in this community of reservoir computing, there is a concept called time multiplexing. Time multiplexing means this system is actually a dynamical system. So we do not need to measure only at a single time. We can take measurement of the system at different times. And therefore, by increasing the number of measurements at different times, we can increase the outcome. And so here we plot the time multiplexing and the number of reservoir. And as we can see, if we measure only at one time, we need a many qubit to reach the fidelity 1. However, if we measure the system, that is the multiplexing, let's say 5 times, then we need only 2 nodes. And similarly for Q3, we need, if we have only measure only one time, we need more than 6 qubit in the reservoir. But if we measure 5 times in time, then we need only 2 or 3 qubit in the reservoir. So by increasing this number of measurement in time, we can increase the number of readout, and therefore we can have a small number of qubits in the reservoir. Still, it should work. Second key question is that if we estimate the density matrix at the output, it needs to satisfy this quantum restriction constraint, that is the phase need to be 1 and positive. And so how do we ensure that? And typically we would like to do this maximum likelihood estimation. And here we wanted to try different, and we said we think that we tried with different number of training samples. So what we see is that if the number of training sample is not sufficient, then indeed some of the estimated density metrics are not physical. They do not satisfy these quantum constraint. However, if we increase the number of training samples, the network actually learns how to satisfy these conditions, and eventually, for large number of training samples, the prediction is always a physical. So we do because the maximum likelihood estimation is computationally very demanding. So therefore, this can be an alternative way to perform this density. Then we tried continuous variable state as well. So here this is the Wigner function for the continuous wave. This is a Gaussian state, and this is Gaussian states. And we can see that we can reconstruct it. The reconstructed error is quite small, and in fact we can decrease the reconstruction error by increasing this number of qubits in the reservoir, and as well as the number of measurement time, that is the time multiplexing. Successively we increase this, and then we see that the error is becoming smaller and smaller. So this is, and then this is actually, I would like to also highlight that this network is quite versatile, and it can do different type of tasks in different settings. So another type of task it can do is quantum state preparation. However, the setting is a little bit now different. So if we imagine that there is a quantum reservoir where there are many quantum qubit type two-level objects, and we are exciting them. And then each of the qubit will emit some quantum state. So imagine that it can be a photonic quantum state or microwave or whatever they're emitting. Each of these nodes is actually randomly connected, and therefore each of them individually will emit some state which is completely useless because they will be random. And then what we think is that if we linearly combine all of these useless quantum states and then train the linear weights, then by combining all of them, we can create some useful quantum state. So this is the idea that we want to linearly combine all of these useless quantum states and create a useful. And so by training, we were able to create some useful quantum states. For example, we could create quantum Schrodinger cat state, or a single photon state, or entangled state. So we can maximize the entanglement such that the output, we can maximize the output entanglement. Similarly, we could create Moon state, cluster state, discordant state. So whatever we want to maximize, we can maximize by optimizing these linear elements. This is one type of task we could do. And the last one, actually, we then thought, okay, to complete this, like at least from our perspective, the story is that can we really implement quantum circuits with such a random network? And this actually, might think that, okay, what is the purpose? Because all we want in the beginning, we wanted to actually avoid this quantum circuit. But we wanted to do that to show that the universality of the system. Can it do? So here we imagine that we have a bunch of again quantum nodes, and they are completely randomly connected through this Hamiltonian, and then we have few computational qubits where we want to perform the these quantum circuits. And these computational qubits, they are connected to this random network through a linear coupling. And this linear coupling, only linear coupling. And then this is how it is done. So we initialize that this qubit state are in some initial state, which can be all qubit are in zero state. And initially the reservoir is also empty. And then the whole system has a Hamiltonian, that this is the random Hamiltonian of the network, and then we couple this with the qubit with a linear Hamiltonian, and then this is the complete Hamiltonian, and there this is the unitary that is representing the evolution of the system. Then we apply the unitary on the input quantum state, and then that gives me the final state. And this is the density matrix, and given by the quantum state. And then to get the quantum state of the qubit, we take a partial trace on the reservoir. So we trace out the reservoir, and then only we have the qubit states. And then if we want to achieve something in the qubit state, for example, we want to get a quantum operation, then we will maximize the qubit. So this is the whole scheme. And then we tested with the single reservoir. So this is a single random reservoir, and we are only tuning this linear coupling with each qubit. We could we could achieve different quantum gates. For example, quantum NOT gate, quantum Y, quantum Z. All of these qubits with fidelity with the same reservoir. We do not change the reservoir. We only change this linear coupling. Similarly, we could do the single qubit gates. We tried with all the gates with the single reservoir, and finally, we after we got this, we see that we could do any quantum gate. Then can we achieve a algorithm like 2-qubit Grover algorithm? So, as we know, the 2-qubit Grover algorithm needs these many quantum gates. And here, instead of applying each of these quantum gates, what we wanted to do is that we want to achieve this whole operation with a single futuring could do that. So therefore, all this rover and operator can be implemented by a single process by this. And then we tried with 3-qubit rover algorithm. As we know, we need 29 quantum gates, including CMOS gates and H gate, H gate, Hadamard gate, and so on. So we need 29 gates. And with this single network, we could do it by only one single operation. And this global algorithm is high level. This is our idea, and then we thought we proposed that using this kind of network, we could compress all these quantum gate and do it by one operation. So this was our story of this quantum reservoir computer, and we believe that this is an alternative way of summary is that we believe that quantum reservoir processing is a way of doing quantum. Because of this high dimensionality of the quantum system, we can have quantum enhancement and here quantum advantage and data processing and quantum estimation, tomography, state preparation, and also implement small quantum circuits and complex quantum circuits. So there are made a lot of and these are few papers recently. So if you are interested, really I would like to acknowledge so I work with this. Some Panjul, Page, and this I would like to thank you.
Okay, thanks for the great talk. Is there any questions? Okay, so maybe I can ask one question. So it seems that many of the results are implemented on hardware devices. Right?
Yeah.
So what kind of platform you're using?
So from right now, everything is done in classical hardware. So there is no quantum.
No, okay.
No quantum because no one did it in the quantum yet.
Okay, so if we want to do experiments in the quantum devices, what kind of platform will be most suitable one for such experiments?
So so our initial actually there are different people are proposing different systems.
Yeah.
So one of this proposal was the first proposal was from this Japanese group, and they proposed this nuclear spin system.
Okay.
And our work was mostly based on quantum dots.
Yeah.
And there are also proposals from with
Okay. Any other questions? Yep.
Excuse me, please use microphone so that the Nagoya side can hear you.
I guess it works now.
I cannot understand. So this reservoir part replaced by the correction of the quantum circuit. So then this is conventional variation of quantum circuit.
Okay, I could be. I'm not familiar with variational quantum circuit. So, but this is actually what I showed is. I do not know. Can you tell me like little bit what variational quantum circuit does?
So I'm not the expert, but in my understanding, that the intermediate part there are so many circuit, quantum circuit, and they want to optimize the choice of the parameter of the circuit. So then they want to make some good simulation or something. So in that case, there are very serious problem for the Plato problem. So they want to optimize the parameter of that quantum circuit, but they often have the Plato problem. So then that kind of method some very serious problem.
I see. So actually here, the key difference would be then that we are only optimizing these few connections and we do not optimize this connection at all. So
You do not optimize that quantum part. You
Yeah.
only optimize the classical part.
yes, exactly.
But I think in that case, the performance is quite limited.
Actually not. So there is this like, okay, so it has been proved theoretically that actually this is an universal approximate, meaning that only by like optimizing this few, you can actually universally approximate any function. And the reason is that actually it's from a observation. When people started learning this deep learning, and you have many layers, actually people observe that in the middle of the layer, actually there is no learning ability actually, in fact. And all these connections you can keep totally random and choose only few connections to learn. And so what this part does is actually it transforms this low dimensional input into a high dimensional system, high dimensional data.
Because, of course, quantum system has so many high dimensional paper. So, but if you introduce a randomized classical system, this one also has some high dimensional data, I think, randomized quantum system.
Yeah, so you can also achieve this with classical nodes, indeed. However, what we observe is that the number of classical node required is actually exponentially large compared to the number of qubits. Because the dimension, if you want to expand the dimension,
No. I'm considering the classical random classical system, random. So distribution, not deterministic. So in that case, you need to prepare so many parameters to identify the classical random variable, classical distribution.
I am not aware of it.
Okay, and other questions? Let's see, they have question.
Can I ask a quick question?
Yeah.
So related to this quantum size up versus classical size thing. So you mentioned that for quantum tomography, fully quantum tomography, you require exponential number of reservoir size, I guess. Is that means if you implement it in fully classical, then you get doubly exponential?
Yeah, so let me. So what we see is that suppose I have this quantum state of n qubit, and then to reconstruct the density matrix, I need n to the power n number of readout. We cannot escape this because I need enough information to estimate the density matrix. So in this case, if we measure only one time, then the number of output is only same as the number of qubit in the reservoir. So therefore, I need exponentially large number of qubits in the reservoir. When we are measuring the system only one time, okay?
Okay.
But if the reservoir is a dynamical system, it is not stopped. So it is still evolving, right? So therefore, I can measure the reservoir at different times. So like 1 second, 2 seconds, 3 seconds, 4 seconds. It's a dynamical system, so I can measure the system at different times. So by measuring the system at different time, I can increase the number of measurements.
Mm-hmm.
So this is so if I measure the system many times, then I can reduce the required number of qubits.
Okay. Do you need to sufficiently wait until the reservoir kind of changes enough?
Yeah, you are right. So this is very important question. So this is also a practical problem. Thanks for the question. So of course the reservoir is also has decoherence. So it's going to forget everything about the quantum state after the decoherence time. And also, as you said, it also need to change sufficiently so that it represents a different measurement. So we have this practicality problem that I have to do everything within this decoherence limit, and I have to have difference between two measurements so that it changes the system. So, and actually the time I need to wait is determined by the Hamiltonian of this reservoir, because if the Hamiltonian the eigenvalues are very large, then it can change very fast, and if the eigenvalues are very small, then I have to wait a long so that it can change.
Okay, thank you.
Okay, any other questions? Okay, so if there's no question, I guess let's thank Sanjeev again. And also let's thank all the speakers in the morning again. And I guess this end of the morning session. Let's see you in the afternoon.
See you in the afternoon.